Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 8, Lesson 6 on area and completing the square. So in our last lesson, we learned how to use the technique or the algorithm of completing the square to solve quadratic equations where you can't just naturally use inverses immediately to undo the operations that have been done to x. But that algorithm, which is, taking half of the linear coefficient, squaring it, adding it on, then factoring it into, like a perfect square trinomial, right? That's a little bit of a mystery. Why does it work? How can we think about it? How can we make sense of it? Well, today, what we're going to do is we're going to take a little bit of a brief pause. Now, I think a lot of what we do today isn't particularly going to show up on any standardized exam or anything like that. It's just a way to make you more comfortable with why completing the square works as a particular technique. So, let's get into it right away and start using area to understand why completing the square works. I mean, it's called a square, for goodness sakes, there should be area somehow in there. So using area to understand binomial products. We've done this many times. But the method of completing the square relies on an algorithm for producing a perfect square trinomial. We can use area of rectangles to understand why this works. So let's begin by doing, really a very much of a review exercise, something that we did as early as Unit 1. Let's take a look at exercise number 1. Use the area models below to find each of the following products. Fill in each rectangle/square with an expression or value for its area, even if the area is negative. Express final products as trinomials in standard form. All right, so we did this kind of thing before as one of the techniques, one of the 4 different techniques we had to multiplying binomials out. So let me do a little review with x plus 3 times x plus 7. So the way I want to think about that is I kind of want to think about x plus 3 as being the length of one of the 2 sides of the overall rectangle, and with it sort of broken up as this being a length of x and this being a length of 3. This is also a length of x and this is a length of 7. Now, of course, to find the area of the overall rectangle, I can just find the area of all the sub-rectangles. X times x, well, that would be an area of x squared. X times 3 would be an area of 3x. X times 7 would be an area of 7x. And 3 times 7 would be an area of 21. If I wanted to find the area of the entire rectangle, I would add all of those together. And as we've pointed out on many occasions, the only 2 that actually combine would be those 2, 7x and 3x would be 10x, and I'd get x squared plus 10x plus 21 as the overall area given to me by that product. Now again, we're just using areas to be able to think about this, but given that we complete the square, right, it kind of makes sense that we might want to try to think about it graphically. All right, we've done this many times before. What I'd like you to do is use that technique both here and here and come up with those final trinomial expressions. Don't use FOIL or double distribution or anything like that. Use this area model, please. Pause the video now. Now, it doesn't matter which binomial you put up here and which binomial you put down here. All right, so I'm going to continue to put the first one up here. I'm going to have x and -2 and x and +5. X times x is x squared. X times -2 is -2x, x times 5, 5x, and 5 times -2 is -10. So my overall area is x squared, or x squiggle, whatever that is. X squared, these 2 combine to be a positive 3x and -10. All right, my final one, I could have x and -4 and x and -10. X times x is x squared. X times -4, -4x, -10x, and positive 40, right? So I'll get x squared minus 14x plus 40. Okay, right, again, very basic review. We literally did this for the first time in Unit 1. Then we did it again in the last unit when we were intensively looking at multiplying 2 binomials together. And now we just start this lesson with it because it's going to set us up for completing the square. All right, now, of particular interest, we'll be seeing how to square a binomial using these area models. And that kind of makes sense given what we've been doing lately. So let's take a look at exercise number 2. Use an area model to find a trinomial expression in standard form For each of the following, fill in each rectangle/square with an expression or number for its area. Now, it's subtle, but I did want to kind of point out that before, in the last slide, right, the overall shapes here were rectangles. They weren't squares, the overall shapes, right? And that's because in theory, if x plus 3 is the length and x plus 7 is the width, or vice versa, right, then they're different, right? X plus 3 and x plus 7 are different. On the other hand, here, right, I'm going to have x plus 5 squared, which is x plus 5 times x plus 5, and x plus 8 times x plus 8, etc., etc. So the overall shapes here are actually squares. So let's do the first one together, right? X plus 5 squared is x plus 5 times x plus 5. So I'm going to put an x and a plus 5 here, and an x and a plus 5 here. So no different than what I did in the last problem, x squared and 5x and 5x and 10. So I'll get x squared, I'm sorry, not 10. Wait, 5 times 5 is 25. So I'll get x squared plus 10x plus 25. All right. And by the way, notice, right, if I look at my final answer, that 10x is broken up into two portions, a 5x and a 5x, right? That 10x comes from two portions of 5x each. Go ahead and square out x plus 8 and x minus 3 using these two diagrams. Pause the video now and take a few moments to do that. All right, let's do x plus 8 squared. All right, again, just to be on the same page, that is x plus 8 times x plus 8. So I'll have x and plus 8, x and plus 8. X times x is x squared. X times 8 is 8x, 8x, and 64. Got it right that time. Let me bring this up just a bit. So that will be x squared plus 16x plus 64. Again, I want to point out, because this is going to be important later on, I want to point out the fact that that 8x and that 8x combine to give me 16x, or if I'm thinking about it going in reverse, right, that 16x can be broken up as an 8x and an 8x. Now, x minus 3 squared is done in exactly the same way, right? That's going to be x minus 3 times x minus 3, if I can tuck it in there. The only difference is I got to worry a little bit more about negatives, but, right, still works out pretty easy. Just watch out for that positive 9. That's going to be x squared minus 6x plus 9. Okay. So, I mean, really no different than the previous exercise. The only difference now is that that and that are the same, which then means this and this are the same. All right. Well, let's take a look at exercise number 3. If the expression x plus k squared was written in the form x squared plus bx plus c, how do the constants b and c relate to the constant k? Well, we could do this with foiling, but let's stick with that area model real quick. Let's think about this for a second. Let's go kind of general at this point. Right? I've got x plus k squared, so that would be x and plus k, and x and plus k, and of course k could be a negative number, so that could be x minus 3 if we wanted, right? And that would be x squared, this would be kx, this would be kx, and this would be k squared. So if I kind of added those all together, I'd get x squared, I'd have 2 of those k's multiplying x, and then I'd have plus k squared. I'm going to put a little parentheses around here, and then I'm going to write that other thing down below. So, if x plus k squared was written in the form x squared plus bx plus c, how would b and c relate to the value of k? Well, b would be equal to twice k, right? And c would be equal to k squared, right? It's basically that easy. And if you look at it, right, that's exactly the case, right? When I had x plus 5 squared, I had x squared plus 2 times 5 times x plus 5 squared, right? Here, when I had x plus 8 squared, I had x squared plus 2 times 8 times x plus 8 squared. And then the same with x minus 3 squared. Okay? So we're all building up to kind of understand why, when doing the method of completing the square, you take half of the linear coefficient and then square it and add it on. Okay? So let's now kind of get into this. When we factor a perfect square trinomial, we're trying to find the binomial that we need to square to get the trinomial. The area model can help us understand where this comes from. So let's take a look at exercise number 4. Each of the following trinomials is a perfect square, meaning it can be written in the form of x plus k squared, where k is some positive or negative constant. Use the patterns you observed in exercise number 2 and number 3 to fill in the models and then write the trinomial as the square of a binomial. All right, so if I look at x squared plus 8x plus 16, right, the idea is I could take that 8x and I could write it as 4x and 4x. Now, why do I do that? I do that, because in my area model down here, right, this little thing here is going to be x squared, right? This little thing here is going to be 16, okay? Now the rest of it has to be taken up by the 8x, and it's going to be equivalent here and here, so it's going to be 4x and 4x, right? Now, what would give me that? Well, what would give me that is if I had an x here and an x here, right? Because x times x is x squared. What would give me a 4x there would be if I had a plus 4 here, because x times 4 is 4x. What would give me a 4x here would be plus 4, because 4 times x is 4x. And then, of course, the 16 would come from 4 times 4 and would give me 16. So that means x squared plus 8x plus 16, which is x squared plus 4x plus 16, is the same as x plus 4 quantity squared, right? That's all. What I'd like you to do is fill in exactly the same kind of thinking in letter B. Go ahead and pause the video now. All right, well again, I'm going to kind of fill in part of this model down here, right? I would have that x squared here, and I'd have that 49 here. But that negative 14x, I'm going to break that into a negative 7x and another negative 7x. And those are going to go right here. Now, that means I'd have an x and an x here, and a negative 7 and a negative 7 here. And then it would all work out, right? Because x times x is x squared, and x times negative 7 is negative 7x, and negative 7x, and negative 7 times negative 7 is positive 49. So, at the end of the day, this would all equal x minus 7 quantity squared. Right? It's like I'm taking the overall area and I'm backtracking out what the side lengths of the square would have to be to give me that area. Now don't get me wrong, you should be able to look at x squared plus 8x plus 16 or x squared minus 14x plus 49. You should be able to look at either one of those and just use things like products and sums to factor them into x plus 4 squared and x minus 7 squared. But what we're trying to do here is give you some rationale for why completing the square works. So let's now get into that. Understanding how to complete the square. We can now use our area models to understand why the process of completing the square works to create a perfect square trinomial, right? So we're just concentrating on that sort of like, why do I take half of the b, square it, and add it on? Why does that produce a perfect square trinomial? That's all we're getting at today. So let's take a look at exercise number 5. Consider the binomial x squared plus 12x. Letter A, rewrite the binomial by breaking apart the linear term into 2 equal terms. Then fill in the area model within the solid lines with the portions of the binomial now written with 3 terms. All right. In other words, right, I can take a binomial that looks like x squared plus 12x. I can leave the x squared alone, and I can break my 12x into 6x and 6x. All right, that's simple enough, right? X squared plus 12x is the same as x squared plus 6x plus 6x. Now in our area model, that would look kind of like that. Now they have to be equal. I can't break it into a 8x and a 4x because literally this is a perfect square, all right? Which means these two portions have to be the same size, which means they have to be the same expression, all right? And that's all I wanted you to do in letter A. Now let's take a look at letter B. Fill in the missing area within the dashed line to complete the square. Write this new trinomial below and express it in factored form, all right? Now, I want to be very clear. I'm going to write down a trinomial which is not equal to this binomial, okay? Right? I'm just going to be adding on another number to fill in this missing area to make that a perfect square. Right now, this isn't even a rectangle, much less a square, okay? But what should I have? Well, how would have I gotten these three portions to begin with? Well, I would have gotten them by having an x here and an x here, and a plus 6 here and a plus 6 here. And so what would end up in here would be 6 times 6, which would be 36, right? Now, that means that, right, x squared plus 12x plus 36 would be the overall kind of square, and that would just be x plus 6 quantity squared. So think about that, right? The 12x gets broken in half. 6x and 6x. Then, where does the 36 come from? Well, it comes from the 6 being squared. Just the 6, not the x, right? The x only gets squared up here in our area model, right? Take half of that linear coefficient, right, which is 6, square it, and add it on, and you literally complete the square, right? Without the 36, the x squared plus 12x is literally this thing, and this thing. But as soon as you add the 36 on, right, which came from taking half the 12 and squaring it, then we have this perfect square, which can then be factored into x plus 6 times x plus 6. All right, so let's do this a couple more times. Exercise number 6. For each binomial below, fill in the missing blank with the number that would need to be added to the binomial to create a perfect square trinomial. Then write it in factored form, fill in the area models to justify. All right, so again, it's kind of cool, right? So I've got x squared plus 20x, right? And again, I can think about that as being x squared plus 10x plus 10x, right? And I'm going to be then adding something on. Right? How does that work out in my area model? Well, I have x squared, 10x, and 10x, which means I'd have to have x times x here, x times 10 here, and 10 here, and then 10 times 10 would have to be 100, right? So I need to add 100 to make a perfect square, and that'll be x plus 10 quantity squared. I am literally completing the square. Right? And I'm completing the square by adding on half of that coefficient squared. Pause the video now and go ahead and do it for B. All right, well again, x squared minus 16x, right? I really want to think about this as being x squared minus 8x minus 8x plus something, right? Again, plus something. So I've got my x squared here, my negative 8x, my negative 8x. That's x times x, and x times negative 8. And negative 8 times negative 8 is 64. That's what I'd have to add on to make a perfect square trinomial. And that would factor as x minus 8 squared. All right. So let's wrap this up. The primary purpose today was to give you a little rationale for why the method of completing the square works. Why do we take half of the linear coefficient, square it, and add it on to the x squared and the x to the first term? Why do we do that? We do that because it produces a trinomial that can always be factored as x plus a squared or x minus a squared. And again, the whole purpose of today's lesson was to kind of give you a visual reason for why that works. This isn't anything particular that you have to like demonstrate or boy, this is an equation solving technique or anything like that. We just didn't want to let that sort of algorithm of completing the square to go unexplained, if you will. All right, so it's basically as simple as that. Now, in the next lesson, we're going to be using completing the square quite a bit in a variety of different ways, but we're going to be getting back to solving equations using completing the square. For now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.